Good morning, and for some of you, also good afternoon. Welcome to this Axiometric Solutions webinar. Today's subject is basic microphone training. My name is Ole Theilgaard, and I'm Director for Global Support and Applications at the two brands at Axiometric Solutions called Audio Precision and Grass Sound and Vibration. The agenda for today is actually a huge agenda, so I think it's a good idea that we start now. Today's training is microphone training, basic microphone training, so we will in the beginning start with an introduction to microphones. Then we will have a look at a capacitor, because a modern measurement microphone is actually based on a condenser principle, so we have to look at the capacitor. Then we will look at microphone principles, how the microphone is actually working and how it is built up. We will look at two main different types of microphones. It's externally polarized and pre-polarized microphones. Then we will look at the design parameters for a microphone. We will see, we will look at the frequency response. We will look at the dynamic range and actually see how these influence on each other and what is possible to adjust a little for changing the sensitivity of the microphone or changing the frequency response for the microphone. We can't talk about measurement microphones without also discussing the standards, so of course we have to have a short look at the standard as well. When we are talking microphones, then we also have to talk about sound fields, how the microphone behaves in different fields. And it means then we will also talk about different types of microphones, free field microphones, pressure microphones, and random incident microphones. We also have to talk about venting of the microphone, because the microphone has to vent to the outside atmospheric pressure, because else it will not work correctly. And in the end, I do hope there will be some time for Q&A, and it will be after the presentation. There will not be, you will not be able to ask during the presentation. Yes, you can ask during the presentation, but you have to wait until by the end of the presentation for having the answer to your question. Okay. Microphones. A microphone is actually a dynamic sensor measuring the pressure fluctuation in the media it is used in. Normally this media is air. If we have a look at the diagram here, then we can actually see that we are all surrounded by an atmospheric pressure. If we have a sound source, it could be a speaker like we have here on the picture. Then when this speaker is making some noise, playing music or whatever it is doing, then we will actually have some pressure variation of our atmospheric pressure. This is this pressure variation the human ear are able to detect, and it's also this pressure variation our microphone are able to detect. It means that the microphone will actually look at both the atmospheric pressure and also at these pressure variations. But due to the venting system in the microphone, then we will actually compensate out the atmospheric pressure, so the microphone output of the microphone is only the pressure variation, the small pressure variation we are picking up by the microphone. When we are talking about pressure or atmospheric pressure, then the maximum fluctuation we can measure is actually equal to the atmospheric pressure. So if we have an atmospheric pressure at reference level, at sea level, equal to 1013 millibar, then the sound pressure level will be equal to 194 dB. Yeah, we can see the calculation here. So the maximum sound pressure level we are able to measure is 194 dB, and it's due to we cannot make a higher pressure than the atmospheric pressure. We cannot make a higher pressure fluctuation than the atmospheric pressure. Types of microphones. See, we have actually three types of microphones. We will start with studio microphones. Studio microphones, they are designed to have a subjective impression. The sound should actually be nice for a studio microphone. We are not looking at a nice frequency response. We are not looking at a very high sensitivity, but we are more concentrating on making the sound of the microphones as neutral and as possible. And a studio microphone should have a nice design so you can use it in television studios and things like that. Other microphones is communications microphones. Communications microphones is all these small microphones we are today using everywhere, in mobile phones, smartphones, tablets, computers, and things like that. These microphones have normally a very low price, but this microphone has actually to be very reliable. Nobody would like to have a smartphone where you have problem with the microphone inside, because the smartphone aren't working. But today we will mainly concentrate on the measurement microphone. The measurement microphone is actually also the reference device used to check, calibrate, and verify both communication microphones as well as studio microphones. So measurement microphones. Measurement microphones are like the two other microphones, a sensor which actually pick up the dynamic pressure fluctuation in air. A measurement microphone has to be reliable. A measurement microphone has to be very accurate, because we will use it for doing measurements. It could be on the communications microphones, for instance. A measurement microphone we have to be able to calibrate it. A measurement microphone has to fulfill the standard for measurement microphone. The standard for measurement microphone is the IEC standard 61094. A measurement microphone has actually a very high dynamic range. It has a dynamic range in the neighborhood of 110 to 120 dB. It has a frequency range which is covering all the frequencies of interest, as long as we are talking about noise and measurements of audio. The measurement microphone is optimized for measurements in the sound field it is used. It means it will have a minimum influence to the sound field. And it will also have a minimum influence on environmental changes, changes in temperature, changes in humidity, and changes in the static pressure. A measurement microphone is normally designed to be used in a heavy environment, to be used in a production environment, in an outdoor environment where you have to do noise measurements and things like that. As mentioned before, the measurement microphone is actually based on the capacitor principle. So let's start looking at a capacitor, a plate capacitor, as we have here on the picture. The plate capacitor consists of two parallel plates, and in between these two plates we have isolation material. It could be a plastic material, it could be oil, it could be many different things. But for a microphone, it is air. So we have air between the two plates. These two plates are charged with electrons. If we go a little further, then there's a nice little formula here, so we can calculate the capacitance of our plate capacitor. The capacitance is actually equal to the area of the two plates times the dielectric constant. The dielectric constant is the insulation material we are using. A different material have a different constant. And then we have to divide this with the distance between the two plates. And by this, then we have found the capacitance of our capacitor. If we go back and say, hey, how does it actually work in a measurement microphone? Then the measurement microphone has actually a diaphragm. It's actually one of the plates. And then it has a back plate. It's the other plate. So it's actually, the capacitor is actually built up by the diaphragm and the back plate. In a microphone, the diaphragm will actually move. It will move due to the pressure fluctuations. When I'm speaking, as I'm doing now, then if I have a microphone in front of me, then the diaphragm of this microphone will actually move. And when the diaphragm is moving, then the capacitance will actually change. The capacitor will change its capacitance. So we actually have a variable capacitor. If we look at the microphone principles, then if we remember for the previous slides, then we have the capacitor. It's between the diaphragm and the backplate, and we have a certain distance between the backplate and the diaphragm, and the diaphragm has a certain diameter, a certain area. So we could actually start calculating the size of our capacitor. Actually, if we look at drawing B here, then we can actually see that the microphone is actually a very simple device. It only consists of a few components. So it consists of a housing. The housing will actually keep everything together. And then it consists of an insulator. It's a little plate making the insulation between the housing and the backplate. And then we have the diaphragm in the top, and to protect the diaphragm not to be destroyed, then we have a protection grid. So that's actually all we have in a microphone, only a few components. We can see another drawing here of a microphone. It's an old drawing, but it's more or less the same components we do have in this microphone as well. If we look at how it works, then as we talked about before, then the diaphragm will actually move due to the pressure variation, and when the diaphragm moves, then we will actually change the capacitance. To a microphone like the one we are talking about, a measurement microphone, we do actually have what we call a bias voltage, a bias battery, as mentioned here. Normally we call this the polarization voltage, and the polarization voltage will actually make a charge, a constant current charge, to our backplate of the microphone, actually a constant charge of the capacitor via this resistor we can see here, together with our polarization voltage, the battery, and then we will have an output voltage. If we look at externally and pre-polarized microphones, externally polarized microphones, it's microphones where we actually have a 200 volt polarization voltage. This is a positive voltage, so we have actually a positive charge of our capacitor, and it means actually if we have a positive signal, then the diaphragm will actually come closer to the backplate. If the diaphragm comes closer to the backplate, then the voltage will actually be less, and it means that we will see 180 degrees phase shift between input, what we have on the diaphragm, to what we have on the output terminal of the microphone. We can also see it here on this graph we have here. Externally polarized microphones are also called traditional microphones or LEMO type microphones. LEMO type microphones is actually due to the preamplifier you normally have to use with these microphones. Actually, you cannot use a microphone without a preamplifier. So with externally microphones, you normally use a preamplifier to supply the microphone correctly. Pre-polarized microphones. It is electric microphones. We have actually no polarization voltage, or we don't need an externally polarization voltage. And this is actually due to we have, so to say, a built-in battery in the microphone. We have actually charged the backplate with electrons. Actually, we have a little layer on the backplate, and this layer has been charged with electrons. Electrons are negative charge, so we have a negative battery or a negative charge on the backplate of the microphone. And it means if we have a positive output for a positive pressure. No phase shift. Like we see it here, and it's actually due to we will have a negative voltage, and then it will actually be more positive because we will come closer to zero as the closer the diaphragm is to the back plate. These microphones are also very often called CCP type or ICP type. CCP and ICP type is actually, again, the preamplifier we are using together with these microphones. CCP means constant current powered preamplifiers. If we have a closer look at the principle, if we remember from one of the previous slides, then we actually have in a power module or power supply, a microphone power supply. In this one, we actually have our polarization voltage, and it's a positive voltage. And this voltage will actually be connected to our preamplifier. In our preamplifier, we have a high resistor, 20 gigaohm in this neighborhood. This 20 gigaohm resistor will actually work as a constant current generator and charging the capacitor in our microphone. And that's a formula that the charge on the for the microphone is actually equal to the capacitance times the voltage. Pre-polarized microphone is actually very similar, but on the backplate we do have a layer. It's actually and this layer has been charged with electrodes, so they are negative charged. You can actually see if you remove the diaphragm, if you have destroyed the microphone and you remove the diaphragm, then on a pre-polarized microphone you will actually see a black backplate, while on an external microphone you will see a backplate in standard steel color. If we look at this little video here, then it will actually tell us a little bit about how the microphone is working. If I start it again, then we can see that the diaphragm is moving. When the diaphragm is moving, then the capacitor here will actually change its capacitance. When the capacitor changes its capacitance, then it's actually due to the distance between the two plates will actually change. If I do it again, we can see, and we can see that Q is constant, and it means actually the V here is actually the output voltage. The output voltage of the microphone, it will actually change, and it's actually due to we have this variable capacitor. If we look at the dynamic range of externally and pre-polarized microphone, then for the microphone capsule itself, then the dynamic range is actually the same. If you use a microphone, it could be a pressure microphone, same size, half-inch for instance, then they will actually have the same dynamic range. They will have the same noise floor in the bottom and the same upper dynamic range in the top for the microphone capsule itself. But we will actually see some limitations, and the limitations is actually more related to the types of preamplifier we are using together with the microphones. If it is a traditional preamplifier, also called the SLIMO type of preamplifier, then we can have up to 120 volt supply voltage. And it means we can have a huge voltage swing of approximately half of the supply voltage. So it's about 50 to 60 volt voltage swing peak we will actually see. For a CCP, the amplifier we are normally using together with electret microphone or pre-polarized microphone has a much lower supply voltage. The supply voltage for a CCP microphone is around 14 volt in this neighborhood. And it means that the maximum output swing we can have for a CCP amplifier is about 7 to 8 volt. And 7 to 8 volt, then we will actually limit our dynamic range of the whole measurement chain, microphone capsule, and preamplifier. So normally pre-polarized microphone will have about 10 dB lower dynamic range than a standard traditional microphone has. And again, as mentioned here, it's mainly due to the preamplifier. If we look at the design parameters, when we're talking about design parameters, then we have to look at frequency response, and we also have to look at the sensitivity. Both frequency response and sensitivity have actually something to do with the size of the microphone. It has something to do with the diaphragm of the microphone. Actually, it's also something to do with the internal volume. The internal volume is actually what we actually have here behind the diaphragm, and the little cavity we have here behind the diaphragm, and down to our insulator. The tension of the diaphragm, distance between the to the back plates, and also the holes, the numbers of holes we have in the back plate. See, if the diaphragm starts moving and we have no holes in the back plate, then it is actually difficult to get to move the diaphragm, because we have some air, and this air will actually make a certain resistance when we try to move the diaphragm. If we make a lot of holes in the back plate, then it will be easier to move the diaphragm, because the resistance will be less. Let's have a look at the area of the diaphragm. Large microphones, they have a higher sensitivity. They have, and it means that we can measure lower levels with these microphones. They have they can measure relative lower frequencies, and they will actually disturb the measurement field more than a smaller microphone. So we will have more diffraction from the microphone, because of the size. The smaller the microphone is, the lower sensitivity, the higher levels we will be able to measure. Higher levels, but also higher frequencies. And of course, a smaller microphone will have less diffraction in the sound field, less disturbance of the sound field because it's much smaller. When we are talking about microphones and we are talking about the design parameters, then we actually have to have a look at the mechanical equivalent for the microphone. The mechanical equivalent for the microphone can actually be drawn. We have a drawing like we actually have here. So we have the mechanical equivalent here, consisting of a spring, a damping, and a mass. The diaphragm or the tension of the diaphragm, it will actually give us the spring. The mass of the diaphragm will actually give us the mass, and the system damping will actually give us, or the back plate, the holes in the back plate will actually give us the system damping. If we look, first of all, look at the system damping. The system damping is actually, like we can see here, this is actually a back plate of a microphone, and we can see all these very small holes. So the number of holes in the back plate plus the volume we actually had behind the diaphragm, actually the volume in here, where I have my cursor right now, it will actually control the damping of the microphone. If we have no damping of the microphone, then we will have a huge resonance peak of the microphone. If we have a lot of damping of the microphone, then the useful frequency range will be very small. So this actually make something in between, so we have a huge useful frequency range of the microphone by having the right amount of holes in the backplate plus the right amount of the size of the back volume. If we look at the influence of the diaphragm tension, it could actually be, we could compare it with a drum, the diaphragm of a drum. If the diaphragm of a drum is very loose, then we can only play lower frequencies. If the diaphragm is very tight, tension is very tight, then we will also be able to measure higher frequencies. Influence on the mass. If the diaphragm is very heavy, then we will only be able to look at lower frequency because it's much more difficult to get this high mass to move. If we look at frequency range for microphone, then the frequency range is normally described as a lower frequency cutoff. The lowest frequency is normally specified at -2 or -3 dB. And then in the other end, we have the upper frequency limit, highest frequency, also here normally specified at -2 or -3 dB. We at Grass produce microphones which actually are able to measure down to almost DC, 0.09 Hertz, up to 140 kilohertz. So we have actually a huge spectrum, not covered by one microphone, but covered by different microphones. Dynamic range. When we are talking about dynamic range, then we are talking about an upper dynamic range. This is the red line we have here, the maximum sound pressure level we can measure with the microphone, and the blue one, the lower limit of dynamic range, also called inherent noise or self noise of the microphone. And again, depending on different size of microphones, then this range will actually change. Like when we were talking about the size or the area of the microphone, then we learned that a 1-inch microphone has a very high sensitivity. With a very high sensitivity, we will be able to measure lower sound pressure levels. But if we can measure very low, then we are not able to measure very, very high sound pressure level. A very small microphone, like a 1/8 of an inch microphone, where we have a very, very small diaphragm area, it can measure very high pressure, but again, the inherent noise or self noise, the lower limit, will again be higher. A typical curve or dynamic range for different sizes of microphones is also described here. 1/2-inch microphone has a noise floor of about 16 dBA, 1/4-inch microphone 35 dBA, and 1/8 of an inch about 50 dBA. The upper limit of dynamic range is actually specified with a max level with a maximum distortion of 3%, and it's a specification in dB peak. And yeah, a 1/2-inch microphone between 136 dB to 160 dB, 1/4-inch microphones 166 to 184 dB, and 1/8 of an inch about 174 dB. The dynamic range is actually the difference between upper limit and the lower limit, and it's typically for a measurement microphone 120 dB. At Grass, we actually make what we call a low noise microphone, able to measure below threshold of hearing, actually down to -2 dB. And in the other end, we make microphones able to measure the highest we actually can measure with a microphone, 193, 94 dB. We have to talk about standards when we're talking about measurement microphones. Yeah, the standard, the IEC 6194, has actually 8 chapters. But for us, chapter 1, specifications, is actually the specification for a primary laboratory reference microphone. It's important, as well as the standard for the working standard microphones, the IEC 61094-4. These are most important. The other part of the standard, the other chapters in the standards, are actually calibration methods, how to do calibrations, where different methods of calibrations are actually described. Sometimes we hear from you, our customers, that you would like to have a microphone which are made according to classifications 1 or 2, or type 0, 1, 2, or 3. Actually, the measurement microphone standard does not deal with classifications, classes, or types. It is actually the sound level meter standards which are dealing with classifications. And it's actually the IEC standard 61672. This is the new sound level meter standard. This one is dealing with class, and the old sound level meter standard IEC 651 is dealing with types. And we have to inform you that it's actually only half-inch free-field microphones for sound level meters, and when you are sitting in US, then it's also random incidents according to the ANSI standards that are described according to classifications or types. So it has actually nothing to do with measurement microphone. But again, most important is the specifications in part 1. This is the primary laboratory reference microphone, and part 4, this is the working standard microphone. If we look into the standard, then the standard describes actually a lot of different parameters around the microphones. It describes the sensitivity. So the sensitivity of the microphone has to be within a certain sensitivity. It describes the frequency response. The frequency response has also to be within a certain level. It also describes dynamic range. It describes the size of the microphone, how big is the microphone. It also describes the maximum influence of environmental parameters, coefficients, pressure coefficients, temperature coefficients, humidity coefficients. It also describes how the microphone should behave on long-term behaviors as well as short-term behaviors. For the LS 2P is actually the primary laboratory standard. 2 means half-inch microphone, and P for pressure microphone. This is actually the laboratory reference microphones, like the grass 40 AU, that's 1. In the standard, it is actually described all these different parameters, and for producing a laboratory reference microphone, then you have to fulfill all these parameters. For working standard microphones, we also have a lot of parameters we have to fulfill. Working standard microphones, WS, working standard, 1 for 1 inch, P for pressure, and if we take WS, working standard, 2 for half inch, P pressure, F for free field, D for diffuse field, and WS 3 is actually for 1/4 inch microphone. So this is for the working standard microphone, and this is actually all 1 inch, half inch, and 1/4 inch microphones that are covered by this standard. 1/8 of an inch are actually not described in the standard, but the manufacturers of 1/8 of an inch microphones, they do all make these 1/8 of an inch microphones according to the standard. So it means that the size is according to the standard. The sensitivity is described. So they're actually using all the parameters for describing the microphone. Sound fields. If we look at sound field, if we have a sound source, it could be a loudspeaker, as we have here in this example, and we place a microphone in front of the speaker in a certain distance. If we place this microphone very, very, very close to the speaker, then we will actually measure a sound pressure level. We will measure some pressure fluctuations coming from the speaker, and yeah, they will have a value. But if we move the microphone a little away from the source of the speaker, then we will actually still see the same value. And we will actually see the same value, almost the same value, until we will actually see that the output of our microphone will start falling with 6 dB, actually falling with 6 dB per double distance. So it means if we are in a distance of 1 meter from the source and we double the distance to 2 meters, then the output of the microphone is 6 dB less. We will actually continue seeing this 6 dB less until we either have measuring the background noise or we are measuring reflections. It could be from a wall. So we are actually now in what we call a reverberting field. Near field is when we have the microphone in very close to the source, and actually typically the transition between near field and far field is typically where we have 1/4 of the longest wavelength. And the transitions between free field and the reverberation field is typically where we actually see 6 to 10 dB higher than the reflection sound. A description here. If we look at again at a microphone in a sound field, and again we are pointing the microphone directly to the sound source. When this is done at low frequencies, we know that the wavelength of the signal is very, very long. And it means actually that a long wavelength compared to the little microphone we have placed into the sound field, then the little microphone will have no influence in the sound field. I mean, if we have a 100 Hertz sine wave, then the wavelength of this 100 Hertz sine wave is 3.4 meter. If we compare it to a half-inch microphone, then the half-inch microphone has a diameter of 1.3 centimeters. So 1.3 centimeters compared to a wavelength on 3.4 meters it is actually nothing. So it will have no influence in the field. But at higher frequencies, where we have a shorter wavelength, let's say 10 kilohertz, at 10 kilohertz the wavelength is 3.4 centimeter. At 3.4 centimeter, then a little microphone with 1.3 centimeter of diameter will actually have a certain influence, and we will actually see that we will build up pressure, extra pressure in front of the diaphragm. It can be shown here. Low frequencies, no pressure built up. Higher frequencies, we will actually see this pressure build up in front of the diaphragm. If we look at it again, we have actually again our microphone pointing directly at the sound source, then we will actually see here, again, a half-inch microphone compared with the wavelengths at different frequencies. Then we will actually see that the influence of using the half-inch microphone pointing at the source is according to the blue graph here. So we can actually see about 20 kilohertz, then we are almost 8 dB higher. So we are actually making a wrong measurement with about 8 dB. If we change the angle of incidence to 90 dB, then we will actually see, if we run this little video, that we will have no pressure built up on the diaphragm. And we can actually see it here. So we will actually, this is the blue line, the blue curve with 90 degrees incidence. Then we have a very flat curve, while the dotted line we have here is actually when we are pointing directly at the source, 0 degrees of incidence. Here it is shown with a half-inch microphone and also a quarter-inch microphone. As we saw before, a half-inch microphone is where we will have the peak top at about 20K, while on a quarter-inch microphone we will see the peak about of about 50 kilohertz. We are actually using this, we looked at before, for describing the different types of fields, different types of microphones, specially designed to be used in different fields. If we look at a free-field microphone, then the microphone itself will actually have this, the little mechanical part will actually have this tendency to have a pressure built up in front of the microphone, in front of the diaphragm at higher frequencies. But we have, from the factory, actually made the microphone, so we actually are compensating for this pressure built up at higher frequencies. So therefore, the free-field microphone are actually designed to have as flat as possible frequency response in the free field. If we look at it, then we saw before, when we place a microphone in a field pointing directly at the source, then we will have a pressure built up like we have here on the blue curve. But in the factory, when we're doing the adjustment of the free-field microphone, then we actually adjust the pressure response of the free-field microphone like the black curve here. And it means that the output we will have from the microphone is actually equal to the red one. It's actually the free-field response. It's actually the output we can measure on the output terminal of the microphone. So the free-field response is actually equal to the pressure response plus what we call the blue curve is actually what we call the free-field corrections. A pressure microphone is designed to have a flat response when it is used in a pressure environment. A pressure environment could be in a little box, in a little cavity, or where if we are in what we call the near field. It could also be if we mount the microphone flush. It could be in a wall, it could be on an aircraft wings, or things like that. then the microphone will pick up the pressure response. And in the factory, when we are doing pressure microphones, then we adjust the microphone so the pressure response is as flat as possible in the entire frequency range for that microphone. Another type of microphone is random incidence microphones or diffuse incidence microphones, also called. These microphones are actually designed very equal to the free field microphone, but the random incidence microphone will actually pick up the sounds coming from all the different angles. So you don't have to point at the source, but it will actually pick up the noise from all the different sources. If you have many sources in a location, then you could actually use a random incidence microphone. It's easier. The random incidence microphone is actually produced and made on exactly the same way as a free field microphone. So we have the pressure built up in front of the microphone. We have the finally random incidence or response, and then we have how we actually adjusted at the factory the pressure response. Where are we using the different types of microphones? Free field microphones. For sound level made up measurements, we use a free field microphone. And here today, this morning, there are a lot of you coming from the US. So in the US, you're actually using random incidence microphone for sound level meter measurement. For environmental measurements and general noise measurements, you will normally use a free field microphones. If you do measurements in small cavities, it could be couplers like ear simulators and things like that, then you will use a pressure microphone. If you mount the microphone in a structure, like we talked about before, an aircraft wing, for instance, then you use a pressure microphone. And it's actually the same if you mount the microphone in or on the structure, then it's a pressure microphone you will use. For measurement in cabins and reverberation rooms, you will normally use a random incidence microphone, but we also know that there are some customers who are using a standard free field microphone. And I can see that it's almost 8 o'clock now. I will speed up. Venting. A microphone is a dynamic sensor, as we start talking about. Measuring the pressure fluctuation in the media it is used, which is normally air. The microphone will therefore compensate for the atmospheric pressure via its venting system. So via the venting system, then we will actually compensate for the atmospheric pressure. So we only are looking at the pressure variation from the source we are measuring at. When you're talking about venting, then there are two venting systems. Either the microphone can be rear vented or front vented. Rear vented, in a rear vented microphone, then we have a little hole from the internal volume of the microphone to the back to the preamplifier, and then we have a hole in the preamplifier to the outside world. It is actually giving us the venting of the preamplifier. If we look at front-vented microphone, a front-vented microphone has a little hole in the side of the microphone capsule. This hole is actually placed below the protection grid, and then the microphone will actually vent to into the front. Where do we use front and rear-vented microphones? Front-vented microphones are actually used in situations where we have a huge static pressure difference between the front of the microphone and the back of the microphone. It could be in wind tunnel applications where we have mounted the microphone in the wall of the wind tunnel. So inside the wind tunnel we have a higher pressure than we actually have outside the wind tunnel. In these cases, we don't want to measure the difference between inside and outside pressure, but we would like to measure the pressure fluctuation we have inside the wind tunnel. So therefore, we have to use a front-vented microphone. Again, it could also be used for measurement in closed cavities, boxes, etc., where we actually see the same tendency. We have a higher pressure or a lower pressure inside the box, and normally atmospheric pressure outside the box. Use of rear-vented microphones. Yeah, rear-vented microphones is actually the microphones you are using if there are no static pressure difference between the front of the microphone and the back of the microphone, and it's actually in most of the measurement situations. What's happening if we plug the venting hole on a microphone? Let's plug the hole, it's done now, and then let's move the microphone up and down 1 meter. If we move up the microphone up and down 1 meter and we have no venting of the microphone, then this 1 meter distance will actually give us a difference in the atmospheric pressure of 0.033 millibar, or equal to 3.3 Pascal. And if we do a calculations, then it's actually equal to 140 B. So by moving the microphone up and down 1 meter, then we will actually change the sound pressure level by 140 B. We can do the calculations here. So this is actually the reason why we actually need the venting. But the venting will actually also take care of the acoustical cut-off frequency of the microphone capsule. And the acoustical cut-off frequency of the microphone is actually depending on the size of the venting hole. Smaller hole give us a very, very low cut-off frequency, almost DC. If we have a large hole, big hole, then we will have a much higher cut-off frequency, and we will not be able to measure low frequencies. This can actually also be described in a standard RC network, where we have R and C. Front and rear venting. Electrical cutoff of microphone capsules and preamplifiers. See, if you look at the electrical cutoff, then it's actually the electrical components we have in our preamplifier. The electrical components between the microphone capsule and the input impedance of our input resistor of our preamplifier. So this will actually give us the electrical cutoff. So we ask for the microphone when mounted on a preamplifier. We have to actually do that to get it up working. Then we are talking about an electrical cutoff, microphone and preamplifier, and the acoustical cutoff, the microphone itself, due to the venting. So the lowest frequency we can measure with a microphone mounted on a preamplifier is actually a combination between the electrical cutoff and the acoustical cutoff. If we look at some challenges, if we could imagine that we have a microphone as big as the Earth, it means that we have a diaphragm diameter of 12,756 kilometers. If we have a microphone like that, then the thickness of the diaphragm will actually be 2 kilometers. The distance between the diaphragm and the back plate would be 20 kilometers. So yeah, that's a drawing here. 2 kilometers thick diaphragm, 20 kilometers in distance between the back plate and the diaphragm. If we apply a sound source with a signal of 40 dB, then this 2 kilometers thick diaphragm will actually move 10 millimeters. And we can actually see here, if we change the level to 20 dB, then it will move 1 millimeter. And if we change it to 160 dB, then it will move 10 kilometers. If you divide all the numbers on this slide with 100 million times, then you will actually have the real data for a half-inch microphone.